there's the recording. All right, everybody see me and hear me okay on Zoom? On Room? Excellent. Welcome back. I would say happy Garbage Day to those of you who celebrate in the Solon or other areas. Cedar Rapids, I think, maybe also has Garbage Day today, I've heard. Let's see. I finished going through all of the Homework 5 plans. So if you did a revision to that, then either I sent you feedback over email or I put a comment in the Icon site saying everything is fine. The way that the scoring is working in Icon is off. You get your 2 points even if it looks like you didn't get them all because 2 points were in one column and one is in the other. Don't worry about that. I'll fix that on my end. The next thing up for bids is formative assessment number 5, which is due Monday night. And we'll go over that Tuesday as usual. And then the week after that, the 22nd, Homework 5 is due, your first drafts of those. And the rule for first drafts of written assignments is they need to be 3/4 complete with respect to points attempted. There needs to be enough there that I can react to it, give you feedback and direction. If I look through it and it is not complete enough, I will tell you that and send it back and it will be counted as late. So the same, in terms of lateness, the same rules hold. It's just -2 points off if you're late, no matter how late you are. However, if you want to be able to do a revision, then I need to have it in time to be able to look at it and then give you feedback that you can then revise by the end of finals week. So just keep that in mind. If things aren't going to come together by the 22nd, that's okay, but try not to let it go too long because otherwise you won't get to revise. And I will give you direct feedback as to, like, for each of the things, you get 2 points for this or you get 1.5 points for this, and here's what I need to make it, 2 points, that kind of thing. The revisions count as late. If it's a late revision, it's 1 point off under normal circumstances, but because it's due at the end of finals week, there's no room to be late. So everything that you've submitted by the end of finals week, I will grade, and you will get an assigned grade based on however many points you've accumulated. You do not have to do revisions, though. I think revisions are very important to the learning process. The rest of your professional career, you're going to get feedback on grant applications, on manuscripts, you're going to get teaching evaluations, you're going to get, do people evaluate you when you give therapy?
Yes.
Yeah, and you're supposed to revise how you do things? Yeah, so learning to take feedback and revise your work or your presentation in response to feedback is a useful skill. So I also want you to not feel the pressure to be perfect on the first try. Homework 5 does not need to be perfect. It needs to have enough there that I can help you make it better if need be. That's all, okay? And it's perfectly fine if you're like, put a comment in there like, "Hi Lisa, I don't know how to do this part. Can you please tell me where I should look?" Like, that's fine, right? I'm happy to have a conversation as part of the evaluation process. And then, what's next after that? I don't even know. I think another formative assessment and then finals week. So yeah, we're closing it down. There is no final exam in this class, just in case you didn't realize that. I don't do tests ever in graduate school. I don't. So during finals week, I will be holding office hours during all of the times that I would normally be teaching or in office hours. So you can find me 4 days out of that week. But we're not quite there yet. Okay. Let me get the beach back. So what were we talking about last time? Tell me what you remember. Words, gestures, phrases, letters, anything.
All the matrix things?
All the matrix things, yeah. Why did I have to do that to you?
I remember that you just gave us one phrase to let us know the big picture to predict multiple outcomes.
Yeah.
Is that correct?
That's it, yeah, that's what we're doing. We are predicting multiple outcomes from the same sampling unit, and I'll say from the same person, just to keep it, simple, but if you're studying, if you're studying universities, or if you're studying organizations, then your unit is that. The example that I have, the unit of analysis is actually a family, and I have responses from 3 different types of people from families, so in that case. But multivariate is the word. So multivariate is a word that some people use in a different way. They refer to multivariate as anytime you have more than 2 variables in an analysis. Like if you have a 1 predictor model You have X predicting Y, they might call that like a bivariate, and then if you have X1 and X2, they'll call that multivariate. I don't use that terminology. I would say multivariable if you were going to go that way, but multivariate to me means multiple outcomes specifically, multiple outcomes from the same unit at the same time. And so there's a lot of situations in which you would see that. And the reason that I had to bore you with the matrices, and I will continue to have to do so to some extent, my apologies, is to describe how the model for the variance has to change to address the multivariate structure. So in this class so far, we focused a lot on distributions and link functions, like what kind of model do you need for Y based on what kind of Y it is? Is it category, is it count, is it continuous, and so forth? We have to be able to extend all of those models to include some way of telling it, hey, let the outcomes from the same person be related. So that's a new concern that we haven't had to address thus far. So the terminology that I introduced, we can review just a little bit of it, which, by the way, I see that some of you are going to come hang out with me in Longitudinal in the fall. That's always nice when I have repeat customers. It makes my heart warm. And if you're thinking, yeah, my advisor's making me, I don't want to, don't tell me that. I'm just going to go with repeat customers on a voluntary basis. That's fine. If you're coming to Longitudinal in the fall, you're going to hear a lot about this type of stuff there too. So we're talking about R matrices in particular. Do I need repeat TAs? Why not? Yeah, I'm not getting a TA for Longitudinal. That's not happening. So if you're interested in volunteering to work for free to pay tuition, as we discussed earlier, then yeah, let me know. But we're going to talk about R matrices because this describes the pattern of variance and covariance across the outcomes from the same sampling unit. So if we start with a model in which there is only one outcome per person, the R matrix that you would have combined across the full sample of just 6 persons here, so it would fit on the slide, has zeros everywhere in the off diagonal. And it has the same variance symbol all along the diagonal. This is another way of saying the independent and identically distributed assumption of regression. The zeros mean don't let these outcomes have their residuals correlate at all. And the fact that it's the same on the diagonal means homogeneous variance, constant variance, no differences in variance across people. The model choices that we have available to us for multivariate data, for instance, if I have 2 outcomes and now 3 people, we add a covariance between the outcomes that come from the same person. And that is assumed to be the same across people, but it allows what you said at, say, time 1 to be related to what you said at time 2. And we can choose for each distinct outcome whether we want to have its own variance for each one like we have here, or whether we can make them the same and not hurt the model. So if we had 3 pictures, then it works the same way, but now we have 3 covariances to worry about across the 3 different outcomes. So we had 3 choices for what the R matrix would look like in terms of what would be relevant to this type of sample. Your choices are unstructured. Let everything be what it wants. No constraints. Estimate a distinct residual variance for each outcome type and a distinct covariance between each pairs of outcomes. This is known as a saturated model in the SEM literature, structural equation models, the class above this, in terms of earlier in the day, I mean. This is also what is used in MANOVA, or the MANOVA approach to repeated measures. This is the type of variance model that it has. When people use those words, however, they are often referring to estimation of these model parameters using ordinary least squares. And that is the problem. Ordinary least squares means everybody has to have every outcome in order to be included, and if not, the whole person gets kicked out. If we use maximum likelihood, or what is known as residual maximum likelihood, which is a slightly different kind that's appropriate for normally distributed outcomes, then we don't have to kick out whole people necessarily. We get to keep whatever data that we have. The other choices are constraints even further. So we can allow different variances, but say the correlation between these outcomes has to be the same, or we could say the same variance and the same correlation between these outcomes. So these are more restrictions on it in terms of what is possible. And this one in particular, the same covariance across outcomes, same variance across outcomes has a special name. It's called compound symmetry, and it is the same thing as the univariate repeated measures ANOVA. That is the variance structure that model uses. And it rarely holds in real data, in my experience. Because if these are different occasions, if people change over time differently, they will spread themselves out as a consequence of that. So the variance has to change over time if you have individual differences in change. In experimental designs, like if I have an easy condition, a medium hard condition, and a difficult condition, I would expect the same thing. People will be closer together in the easy condition than they would be in the hard condition. So any of these constraints in terms of what we can make the same versus what we shouldn't is answerable with the likelihood ratio test. So these are all choices that we have. There are many, many, many more kinds of R matrices though. So like if you look up the SAS repeated statement, there's like 36 options listed. There's different ones that are more appropriate or useful for when the repeated measures are time, and also repeated measures as space. So like geospatial data, like if you have outcomes that are located in 2 or 3 dimensional space, the ones that are closer together in space are more related. So then you can build in correlation patterns based on distance in multivariate space. There's all kinds of cool stuff, but we're just covering the ones that we need for this example. We're skipping that stuff for now because I still don't have the strength. Talked about testing differences in effect size. I'll show you how to do that. And then we started talking about fixed effects parameterizations, and I promised I would re-go over this as if you never heard it before. Parameterization is a fancy word that means how you set up your model. So you could also say specification. I think that one works as well, but parameterization is a phrase you will hear commonly. So there are 2 main ways to set up the fixed effects in your model for these multivariate cases, and it depends on whether you're going to allow a general intercept, like typical, or a different intercept per outcome. So general, this is slide 32, I'll pick up on. Maybe. There we go. We'll see. Okay, and the TV's still working behind me. Awesome. This is what you're used to doing, with some catches. We are used to thinking about, for instance, a categorical predictor. Let's say that you have a 3-group variable where someone could be in group A, group B, group C. We would need to put in 2 different dummy codes and give them fixed slopes to be able to differentiate across the 3 potential group means. And there are various ways of coding those dummy codes to represent different comparisons. It's up to you however you want, but you need to. The exact same thing is happening here because from the software's perspective, it doesn't know the difference between A, B, and C groups across people or A, B, and C outcomes within a people. The latter, we're addressing by additionally adding those patterns in the R matrix that allows these things to be correlated. But from a fixed effects, it don't care. It doesn't need to care. So if I think about these as just traditional dummy codes, where this is a 1 if it's A, and this is a 1 if it's B, and 0 otherwise, that means that my fixed intercept here, which is not attached to anything, it's beta 0 all by itself, that has to be the expected outcome for the reference DV, which is C. So you can think of it as group C if it's easier, but the outcome is C. So that means then that beta 01 and beta 02 take on the usual group mean difference interpretations. Beta 01 tells me how different the A outcome is on average from the C. Beta 02 tells me how different the B one is from C. That means that if I wanted to know the difference between A and B, that's a linear combination, beta 2 minus beta 1 to get that one. Likewise, if I wanted to know what the intercept was for C, those are linear combinations of the general intercept plus the deviation for that specific outcome. If I wanted to add a predictor, then I have the same type of pattern. I have a main effect of X, and then I have what looks like X by dV interactions. So for the same logic, the main effect of x, beta 1, 0, is specifically for the C outcome, because that's when these other two would drop out, when they would zero out. Beta 1, 1 is going to tell me how the slope of x differs in the A condition from the C. And then beta 1, 2 tells me the same thing about the B condition relative to the C. So when you would want to do this, do you remember the examples that I gave? Or can you think of other ones when this type of setup would be useful? Any ideas? I'm eagerly watching the chat, or the Zoomers may talk to me. We can hear the Zoomers in the room, because that's how the audio works. No? Do you remember the body image thing? That was one example I gave. Where you were asked on a 10-point scale of stick figures which one you look like, and then you were asked which one do you think you should look like, and the researchers did not care what they picked. They cared about the discrepancy. So if you think about the concept of like dissatisfaction with your body as what you're measuring, that is captured by the difference between conditions. This specification would directly tell you about that, because beta 0, 1 would be the difference between like what you should look like and what you do. And in that example, there's only 2, so there wouldn't be a B. Likewise, if I wanted to know if body satisfaction differed as a function of gender or age or anything else, then that is telling, the interaction term directly tells me that, because this is the difference that indicates dissatisfaction, and then this is the moderator of that difference. So any individual characteristic could moderate the extent to which you are different in terms of how you perceive what you should look like and what you do look like. This would hold equally for any time that a condition mean difference is the thing you care about. So in the divided attention literature, for instance, every experiment is set up in basically the same way. You have to do a task where you do only that task, and then you do the same task while you do something else. Like you might have to teach while looking down at your monitor and your room to figure out who you're talking to. Or you could just teach to the room. And the difference in performance under the condition in which you're doing more than one thing versus when you're doing one thing, that's what people care about. That's the divided attention cost. Well, beta or DVA would tell you that exactly. The difference between conditions is right here. So if you want to know if there's a bigger cost to a hybrid class for pre-tenure faculty instead of post-tenure faculty, right? That could be X, hypothetically. That is not an answerable question to me, because hybrid was not a thing when I was going through tenure. Zoom was not a thing. It's kind of crazy to me to think back to those days when you had to show up at campus all the time. Anywho. All right, we doing okay with this idea? All right, so I'll show you examples where things are set up in both ways so that you can compare and contrast. This is just kind of a generic way to talk about it. So here's how I would feed in this information in terms of the fixed effects. For instance, here's what it would be in SAS, here's what it would be in Stata. So I have my outcome, and I have my dummy codes differentiating the conditions of my outcome, which outcome it is, and then I have the predictors. The rest of this stuff we'll talk about later on. You can ignore that for right now. By the way, what is Y? I forgot to review that part. If I'm predicting A, B, and C as 3 different things, what's Y? How am I tricking my software to be able to do this? Do we remember that part? There's a data transformation step that has to happen before you do any of this, and I will show you how to do that as well. Let me go back to where that is. A ways ago, I think. Maybe not that far. There it is. This slide. Slide 9. So in order to fit multivariate models in software that is expecting one outcome, you have to stack all of your outcomes into one column. The result of that combining all the outcomes into one column, I'm naming Y. So in this example, there are two outcomes per person, one row per person. This is what's known as wider multivariate data. We have to restructure it by transposing per person so that it becomes one row per outcome per person, what is known as long, or person period is another synonym. I call it stacked usually. So we have one single outcome then that holds the multiple outcomes per person, and we need to have another indicator as to which outcome it is. So in the DV example, back to this, I had stacked outcomes A, B, and C into one column, and then created the dummy codes that identify which is which, so that they can act as switches to essentially turn fixed effects on or off in predicting each specific outcome. All right, here's an alternative that has less typing. I deliberately hide this from people in my classes, I'll just say that. I do, because I think it makes it harder and more confusing when you're first getting started. But every software package, start here on slide 34, this is the slide I skipped over last time, we'll do it now, is the alternative way of explaining to your software that a variable is to be treated as categorical or discrete, or what is known as a factor variable in our language in particular. If you tell it that, then this dummy coding that I did manually happens for you within the software. Come back. Come on. Oh, too far. There we go. So it creates internal variables that essentially mean the same thing for these. And then the question is, how many of these get put in the model? If you have a general intercept, one of these columns is redundant. You don't need all three. You can't have 3 group-specific slopes and an intercept when there's only 3 groups. So then the question is, which one is going to get dropped? In SAS and in SPSS, the last one becomes the reference because the last one gets dropped. In Stata and in, I think in R, it's also the default in at least the packages I've seen, the first one gets dropped instead. So if the last one gets dropped, your reference group would be C. If the first one gets dropped, your reference is A. But this would remove the necessity of making all these different separate dummy codes. Like if you have 10 outcomes, you don't want to type that much, right? You'd be like, hey, it's 10 things, make it work. And I don't have a problem with that once folks know what they're doing. But when you first start coding things, for instance, here's the version of the model where the dummy codes are written out manually. Here's the version where they are not. So I'll focus on the Stata code here. I have iblast.dv. What that is doing is saying, hey, take this original dv variable that is A, B, and C, and make the last category the reference, and kick the last one out. That's the B part. So I'm making it so that the default is the same as what happens in SAS, but you could have the first one be the last. So then the effect of X interacting with DV is specified the same way. So whereas I had to write those things out here, or here I should say, I didn't here. Now here's why I don't like this. If you're just getting started and you don't know much about software and what the choices are, because obviously this is not transparent, right? If software were easy, I wouldn't have a job. How many things do you think DV is in terms of parameters if you just list it once? It looks like one thing, right? No, this is 2 things, and you just have to know that. And you have to know what they mean, because it differs by model parameterization and it doesn't necessarily tell you that. So to me, this is a less transparent way because it doesn't align with the linear model representation, but it's much more convenient once you know what you're doing. Because software also, when it understands that DV is one column of a categorical variable, there are easy commands like, hey, do you want all possible differences? Sure, thank you. As like one line of code as opposed to every possible combination that you would have to write out. in R, I didn't forget y'all, don't worry. We're going to be using GLS for these models. That is within the NLME package. And here's the manual way of writing out the dummy codes and the interactions with the X predictor. And then you can use factor as a function for your DV if it's not already labeled as a factor variable in your data set. And C, by the way, is another version that I recoded so that the reference would be the first one, made it first. So like that. Okay. How are we doing? How are we doing? I should say more articulately.
What do the correlation and the weights mean again?
Yeah, we haven't talked about that yet.
Oh, we haven't?
Nope.
Okay, I thought maybe we did. But
I mentioned it briefly, but you haven't seen it in action.
Okay.
So this is going to ask what pattern you want your R matrix to be in terms of the off diagonals, whether you want them to be not there, the same, or different, or basically the choices. And weights, you would think that that has to do with sampling weights or something like that. It doesn't. It has to do with whether you want your variances on the diagonal to be homogeneous or heterogeneous. No, they're not weights. But maybe all the other like reasonable choices for words were taken. I don't know. You'd have to ask the people who made it, but that's what it means. I can, since I did it in R, I can talk about it in Stata for a second here. This is a whole long thing. So new code. Stata users, this is a long-standing convention that I don't think you have to do anymore, but I keep it so that everything is backwards compatible. Stata doesn't have a line terminator. Like you see how SAS has semicolons that tell it like when you're done with something. It doesn't. It thinks the end of the line is when you're done. So to make it keep going, you have to give the 3 slashes. So this part you're used to seeing. Mixed is a routine that you haven't seen yet, but it's basically a standard general linear models that include multivariate choices routine. This bar person ID colon thing is how you tell Stata how the R matrices should be defined. So like how do we group the rows together? Each person ID gets their own R matrix, essentially. Stata by default, when you do this, introduces something called a random intercept into the model. I don't want that in this particular instance, and so I have to shut it off with this no constant option, which is referring to the random intercept specifically. There's a separate one for fixed intercept. Variance is here because by default, Stata printed standard deviations for the longest time, and I wanted variances so they'd match. I think that default may have changed, but I'm not for sure. REML is a type of estimator. That is also a default in other things. We're going to use that. Degrees of freedom is a thing once you get into multivariate models. This is one way of estimating them. You can learn more about that in the longitudinal class. And then residuals, that's your R matrix command. So the question marks is which pattern you want. So there's choices called independent, which means no off-diagonal stuff, exchangeable, which means all the off-diagonal covariances are the same, and unstructured. So like the three patterns we talked about. Last but not least, TDV means how is the R matrix within a person structured. That is necessary if you have incomplete data. So if you don't have that there, it'll be like, okay, first row for person 1, got it. Second row for person 1, that's time 1 and time 2. But if they're missing time 2, and the second row is supposed to be time 3, then it's going to be put in the wrong spot. So this just makes sure that it understands which rows are complete and which rows are incomplete with respect to that. And for any SAS users in the house, class statement is how you tell it that it's a factor variable in SAS. So, okay, did I answer your question about what that is for? Any other questions about code? And I have some of this written in the example that we'll do, but since we're talking about it now, that's fine. All right, Zoomers, am I frozen? No, okay, good. Because you looked frozen for a minute there. I was like, uh-oh. Nope, just very, very still and attentive. I understand. Okay, so this is one way of doing things. Come on, you can advance PowerPoint, you can do it. All right, one more. There we go. Here's the other way. So let's say that you're not interested in differences across conditions as the thing you care about. Let's say that you're more thinking about these as just 3 separate outcomes. The example that I gave, I promoted myself to clinical psychologist last time. I was a clinical psychologist earlier today as well. I'm going to do an intervention that's going to fix people, going to make them all the way better. And I'm going to fix their anxiety, their depression. I'm going to improve their well-being, and I'm going to reduce their negative affect. Okay? Those are different things on different scales. I don't know, like, I wouldn't want to know, are you more depressed than anxious? Like, they're not, you wouldn't ask for mean differences because they're different things. So if you're thinking about your outcomes in this way, then this is an alternative way of setting up your model that's going to be much easier to work with and more useful. I call this DV-specific intercepts, dependent variable specific. The difference is entirely in what happens to beta 0. This change has a lot of downstream consequences in what the model terms mean. So there is no more general intercept in the model, meaning there's no more beta 0 sitting all by itself. So what these become are essentially switches that turn on when you want the fixed effect to apply to that row as a 1, and then turn off when you don't. So beta 0, 0, because it's attached to this filter, the switch, is now specifically for C like it was before. But these two are no longer differences because beta 0 does not contribute to their outcome. They're on their own. So now this is just the intercept for A and this is just the intercept for B. So to me, this is a hell of a lot easier to think about. Like, and it's literally the labels, right? Like this is the C1, this is the A1, this is the B1. That means that I have 3 parameters given, 6 that I'm interested in, but the ones that are given are different. Now I get the intercept for each directly, but there's nothing in the model that directly tells me if they differ. That's all right, I can find that out. Linear combinations for the win. Mean differences. Same principle if I add a predictor. There's no main effect of a predictor all by itself, in the same way there's no main intercept all by itself. No main effects of predictors in this version of the model. Instead, we have these switches. So beta 1, is the slope of x for DVC. The next one is the slope of x for A, and this is the slope of x for B. Like, just picture light switches in your head. Just like flip it on, applies to this row. If it's a 0, flip it off. Maybe not flip it off, but, switch it off. Yeah. I misspoke. I try to keep it clean, but, Any differences in how the X predictor relates to each of these outcomes then is a linear combination. So if I wanted to know if my effect of my intervention was better for anxiety than depression, I could find that out of these linear combinations, assuming that my measures are on a comparable scale. So I'd have to z-score them or something like that first in order for these to be meaningful. Here's what this would look like in code. So the difference is underlined here. You have to manually shut off the general intercept because it is a default. So there's 2 different no constants in the state of code at this point. The one that is underlined is the new one. This refers to the general fixed intercept that is no longer here, and that's why I have all 3 dummy codes in here instead, and then all 3 interactions with x, which is just the slope of x for each one. The second no constant is still with respect to the random intercept that we don't want and don't need to deal with at this point. The factor version of the model would look the same. The switch is really this no constant. Okay. Stata folks, does that look reasonable to you? So we add the no constant, and then we have the C condition explicated here rather than as a default reference. In R, you just stick a 0 in. I love this. It's like, well, how do I take this 1 and make it not 1? I don't know, make it a 0. It worked. Beautiful. So you're just like, no intercept, please. Now I'm going to have 3 distinct intercepts, and I'm going to have 3 distinct slopes of x. All right, you can mix and match, but carefully. this can get ugly real quick. So here's an example. Let's say that I want to have x1 as a predictor, and I want it to have different slopes in predicting all three outcomes. Cool, I can do that. But for x2, I don't want it to predict outcome C. I only want it to predict outcome A and B. Can I do that? I just did. You can do whatever you want. So this might be if I've already know that based on previous analyses that x2 doesn't relate to C, like that might be just something I don't need in my model. It could also be the case that it's not measured for C, or it's not relevant for C, in which case you would fill in some constant for it so that it's not, those cases aren't kicked out of the model, but there would never be a switch where it would be turned on for C. So this pattern of fixed effects is what I want, and here's what it would look like to do that. So if I'm using a general intercept, then everything is given for C, and all the other terms tell me how it's going to differ for the other outcomes relative to C. So these are the differences in intercept. This is the x1 slope for C, and these are the differences in the x1 slope for the others. So if you add the main effect to each of these interaction terms, you get to what it would be in the other one. And then these two are the slope of x2 for A and for B. There's a hole here. I did that on purpose. So even though this part looks the same, like x1 section and the x2 section, these are different. They don't mean the same thing. Because I have this main effect of x1 here, beta 1,1 and beta 1,2 are differences in how the x1 predicts B and A relative to what it is for C. Say that again. Because I have this beta 1,0 main effect of x1, that is specifically for C. Beta 1,1 and beta 1,2 tell me how the slope of x1 differs for B versus C and A versus C. So through linear combinations, I can get to what the slope of x1 is for A, for instance, if I add together beta 1,0 and beta 1,1. And if I want to know what it is for B, it's beta 1,0 and beta 1,2. Now on the last line here, there's a hole. There's no like what it is for C because I didn't want that. So these are not interaction terms, even though they look like they should be. This is the slope of x2 for A directly. This is the slope of x2 for B directly. Because there's nothing here for them to deviate from. And you're looking at this and you're like, how would I know that? I know. This is why you got to be really careful mixing the strategies together. But you can set it up however you'd like. The DV-specific version, I think, is more transparent in that everything in here is directly for the thing that's next to it. Like, these are the intercepts. These are the x1 slopes. These are the x2 slopes. The end. So that's why I like that one a little better. By the way, in path analysis, which is where we're going to end up, this is how they do it. In path analysis, for every variable in your model, you tell it, I want this model for this variable. I want this model for this variable. You don't have to be like, well, I'm going to make one of them a reference, and then the other is going to be how far off from that reference it is. Like, none of that. All right. Let's see. Nikki, did you take generalized in 22 or 23? Do you remember?
I think it's 22.
Okay, then you would have done the pancakes and crepes homework over this. Do you remember that? I have this homework that's the most evil thing ever, and it's about pancakes and crepes. There's a story. So it was going to be training in how to make pancakes and training in how to make crepes, and then you have to make each of the other that you weren't trained in. And the story was based on my husband getting into making crepes as like a fun thing to do. And it turns out that the skills you need to make a crepe are not the same skills you need to make a pancake. They don't turn out very good. So I had this whole design where there were only 4 different values, and then there was which treatment were you in, and all these different questions about this. It's epically horrible. And I actually quit doing it and built in the individual data analysis instead for homework 5. The reason is because not only did people hate it, but I feel like this sort of thing where you're having to reverse engineer what you want is not used as much anymore, so it's not as needing for a skill. But if anyone's looking for a challenge, I'll let you have it. Pancakes and crepes. Okay, wrapping up. Woohoo! So, big picture, and then I'll show you a little bit more specific examples with parameters and stuff. When each person or each unit of sampling has more than one outcome, that's when we need multivariate models. We're going to start with all the same ideas, concerns, needs, and language that we had for univariate, but then add to it the idea that the residuals from the same person need to be correlated. How do we do that? We choose a pattern of our matrix that we want. Are the variances going to be the same across all the outcomes? Are the covariances going to be the same across all the outcomes? Those are the choices. To decide, we use likelihood ratio tests. The reason that we care is that our fixed effect standard errors are going to be a direct result of whatever type of R matrix we have. If we pick compound symmetry, then the standard error is going to be like essentially the same, like the ingredient that goes into it is going to be the same because it starts with residual variance. So that means that if the outcomes, some of them have more variance and some have less, then standard errors are going to be off in different directions. We don't want that. For other outcomes, which I'm not doing today, the other way of introducing dependency is what's known as random effects. So that's the thing that Stata puts in there by default that we were shutting off to do it this way. We'll do that more later. Fixed effects can be specified in different ways, whether you have a general intercept that indicates differences, or whether you have one intercept per outcome, which indicates then switches. So path analysis is like the next big thing, but I think I'm going to do the littler thing first. I think I'm going to change my mind. I'm going to post the thing that I called bonus coding example that I put on the website for today. I'm going to pull that up. I built this in 2020, actually, so I haven't actually had a chance to look at this in a long time. So this is on the website for today as a Word document. So I wanted to do a little bit more with this idea of general intercepts versus outcome-specific intercepts and show you how that would work in a more complex case. So let's say that I have this design. I would call this like a 3x3 design in ANOVA type language, factorial. So I have one dimension that I'm calling 1, 2, and 3, and one dimension I'm calling A, B, and C. That's all we need to know. So what I would want to know out of this is, are there differences across the numbers within each condition? Are there differences across the letters within each number? And then, for instance, is that difference the same as that difference? And is that difference the same as that difference? And so on. So there's a whole lot of different things. So if I set up the model in the standard way to have a general intercept, then I would dummy code so that, let's say, I'm going to have this one be an alternative group, this one be an alternative group, B and C will be the alternative groups, and that means A1, that combination is my reference for the model. So the fixed intercept is going to tell me the expected mean for the A1 cell specifically, and all of the others then will be some deviation from this cell as the reference point. So here's what the contrast would look like that make this work. I'm going to name one A versus B and A versus C, another one 1 versus 2 and 1 versus 3. Okay. So here's the model that I would need to get all possible interaction terms and main effects that would create 9 different expected outcomes across this combination. I need 9 parameters. Then I will get each of these means exactly right. So here's the 9. General intercept. Beta 1 and beta 2. Those are simple main effects about the letter dimension, specifically for column 1. Those are going to tell me about those differences. I've also got these simple main effects, which are going to tell me about the number differences across the A row, that one. And then I've got how the letter differences differ by number. Those are interactions, differences in slopes. So I've got 4 of those that are possible. And the others are then consequences. So I only need 4 parameters to get all 6. So I've got my 9 parameters in this model that's going to perfectly recreate these 9 cell means. And I can get any information I want about what the cell means are, what the differences are, and so forth. And I did that for you. So here's how the model would recreate the cell means. So here's my reference. The main effective letter, get me this one. The main effective number, get me this one. And then each of these starts with those as ingredients, but adds in the interaction term that allows this difference to be different than this difference. And how this difference is different than that difference. And so forth. And I wrote them all out. So there's a very direct, like, how do I know how these things differ based on this model? Now, this is all well and good. It's complicated, but life is complicated, right? Now, so where this example came from in my head is a real story. I had a student come to me once with a design like this, and she said, what if my ANOVA has a hole in it? She didn't have that one. Didn't exist. All of this falls apart because then only certain combinations are logically possible with data. And you cannot set your model up in the traditional way with a missing cell. You got to get creative. So here's what you could do instead. Just say, screw it. Each cell gets a mean. The end. I'm going to make 9 dummy codes, 1 for each combination, and I'm going to stick them in the model directly. That's still 9 parameters. It's still going to give me my 9 means, because the result, using all the fixed effects, intercept, main effects, and interaction terms to build the means is one way to do it. Doing it directly is another. So then it's just a question of, what do I want to know? Well, here's like one difference. Are those 2 things different? And then, is this difference the same as that difference? It's just linear combinations of all the different means to answer all the questions. So if you have a design that's really complicated and you don't have every possibility observed, this can save you. It's also just more intuitive, I think. This part might be a little bit less so, but certainly getting the means out of the model directly is a useful thing. So in the pancakes and crepes, this is what I told the kids to do. Do it that way. Where I have used this in practice, beyond just the ANOVA as a whole in it, is for SMART designs. I forget what that stands for. Probably not the same SMART that you're thinking of. What happens is when you're doing an experiment and you randomly assign people to intervention conditions, and then you check on them halfway through, and the ones that the intervention is not working for, you assign them to a different condition. It's sequential, multiple, adaptive, randomized something, I think. SMART is the acronym. That's what I got. Well, that kind of design where certain people can only be in certain cells based on their prior performance, I fit with something like this. It's like, all right, how many combinations do I have? I'm going to give each of them a mean, and then I can use linear combinations to figure out what the differences are. When you have nested data where not all things are possible, then figuring out what the corresponding main effects and interactions would be to work with that is much harder. So if anyone ever has to deal with that kind of design, let me know and I'll hook you up. So in the multivariate stuff, I'm doing it this way for the most part. What is it for each outcome? Just tell me that. It makes life a little bit easier. Okay, how are we doing? Zoomers, hanging in there? Do you have the strength for an empty model with real data? I'll just ask it that way. Do we have the strength? taking a vote. Who has the strength for an empty model with real data? Who doesn't? One person says they have the strength. 2 people have it or don't have it? Okay, have it? Show of hands or votes? Okay, 3 people. You're like, all right. Okay, well, no one else is voting no, so it looks like it's unanimous. Yay. I have unanimous approval of the 4 people who answered the question. That reminds me of course evaluations. The 2 people who answered it love me. Well, I don't have that problem. You'll find out why in a couple weeks. Foreshadowing. All right, so this example is example 5. This comes from real data, which is why it's not, the data themselves are not in your download packet. This was part of a study that I assisted with when I worked at Penn State as a postdoc and first started teaching these models. So I was in the human development, what was it? HDFS.
Human Development and Family Studies.
That's it.
That was my undergrad.
Okay, were you at Penn State?
No, I was at Iowa State.
Okay. So yeah, I was actually in the gerontology center, but like that was, most of the people in there were from that department, so I just sort of claim HDFS. But point being, there was a whole lot of people collecting family data longitudinally. And so that makes for a perfect example of these kinds of things. This is not the longitudinal class. This is the generalized linear modeling class. So we're just going to use one occasion of data for this example, but I'm using 3 family members. So the story is, these are a very specific kind of sample in which for each family they recruited the mom, the dad, and an adult child. So obviously this is only meant to reflect heterosexual couples who never got divorced and had children. So a subset of the world. The outcome that we're predicting is a scale mean, so an average across items, and the items were on a scale of 1 to 4, about gender roles in marriage in which higher scores indicate more conservative attitudes. So what should women be allowed to do kinds of questions. This is sort of older data, I would say. This is probably collected in the 90s or early 2000s. Now, even though my outcome is bounded between 1 and 4, I'm going to start with predicting pretending that it's normally distributed, and then we'll see what the impact is of ignoring that later on. The reality is that to do this as a binomial, which is what it would need to be since it's continuous from 1 to 4, there's not very good multivariate options for that. So I couldn't do it the way I wanted, but I have checks in to make sure that it's not too wrong at the very end of this. So I am going to be using 2 different predictors, essentially. The gender of the adult child, and I have that labeled as girl, boy, even though it's an adult, and the years of education of each family member, centered such that 12 is the reference, so a high school degree. So that's it. That's the story. We're going to predict all 3 outcomes simultaneously, first by tricking univariate software and stack data, and then I will fit the exact same models as path models so that you can see the correspondence. So that's why this is part 1, is what we're looking at right now, and then part 2 will happen in a couple of weeks. So the first thing that we have to do is to reshape the data. So this is what it looks like. This is a SAS data set, but it's the same principle in any program. So for family 3996, for instance, here's all the data I have. I have the gender of the kid. I don't need the gender of the parents because in this case it's tautological. I have a mom and a dad, and that's how they were coded. I have the education of each person, and then I have the outcome for each person. So in this family, for instance, the kid is very egalitarian, mom is less so, but dad is, and dad is more conservative in this family than either of the other people, and so forth. So what I need is to take these last 3 columns and turn them into 1 column. This is the end result of that coding process that I'll show you in a minute. So now the first family has 3 rows. Everything that was already there is still pasted down the rows. It has to stay that way. I created a new, essentially a categorical labeling variable for who was who, as well as the 3 dummy codes for which outcome it is. And then here is the outcome. I'm calling it marital since that's the same measure across the 3, and all 3 scores are stacked then for each family like this. So I had to make these ending variables myself. These ones were already there as part of the data set and got pasted down. This version of the data, though, is what path models use. The wide data is what you need for path analysis because you're going to tell it, hey, predict kid marital with this, predict this one with this, predict this one with this. But univariate software is like, I need one column, so you got to give it one column. Okay, so here's how I did that. In Stata, there is a function that's called reshape, but it's very specific in how it wants your variables to be named. So I started out with variables that were called kid marital, mom marital, and dad marital. And Stata is like, no, I don't know what you're talking about. Okay, how about if I call it marital 1, 2, and 3? Yes, that's correct. So it understands that if you have a common stem like this with a number after it, that they're all part of the same thing and that you want to transpose them. It did not understand that because of the way I named the variables. And after an hour or so of going through the documentation and the help manual, I was like, screw it, I'm just going to change the names of the variables. So there may be a more principled solution to this, but I was not able to come up with it. So I did that first, and then the reshape command is, which way do you want to go? So I'm going from wide to long. What is the name of the stem of the variable that you want to stack into one column? So I say marital, and then it goes through and looks for all the ones that have marital in the front. And then what is the index that tells you which rows go together? Family ID. So that was the variable that I had right here. And then how do I index the repeated observations? I'm making a new variable called DV number in this case. Then I made it the way I wanted. So I first generated dummy codes where I set to 0 as an initialization, and then I turned them on to 1s if for each of these. This, by the way, would not be good if I had missing data, but I filtered the data set to be complete so that I didn't have to worry about that. Otherwise, I'd have to deal with missing data in this case. So I have kid, mom, and dad as my switches, essentially for turning on each outcome, and then I have the labels in here as good practice. In R, I'm importing a SAS dataset into R, since that's how I had it stored, using a package I found called Haven, which is read SAS is one of the commands. They have in base R a command called reshape. So you don't need the tidyverse for this. You can just use base R just fine. It wants to know what data set you'd like to reshape, which way you want to go. So the same idea here, I'm going to long. What is the index that keeps track of how the rows should be connected? Family ID. Varying. These are the things I want to stack together into one column. I'd like to call that column marital, and I'd like to call time var. They're anticipating this being longitudinal data, but it doesn't need to be. I'd like to make something called dvnum, and I'd like to use these numbers. So then dvnum is 1, 2, 3, and then I made the same kid, mom, and dad switches the same way, and then selecting for complete cases. All right. Okay so far? You will not need to do this for homework, but if you need to do this in life and you can't get it to work, please let me know and I can try to help you. In SPSS, there are commands to do this as well. So every package I know of has a way to do this type of reshaping long to wide, wide to long. All right, first up, empty models. I promised you, right? Just 2? It's 2. I don't want to push it with the strength thing. So I'm going to predict marital, and I have FI as my subscripts today. You are allowed to pick whatever letters you want for subscripts, by the way. They don't have to be I, T, or J. That's just a thing. So do you know what F stands for? Family. You know what I stands for? Individual. I could have went with P, but you know, FI. So this is the general intercept version of the model, where I'm thinking of a reference outcome, and then I get differences for the other outcomes relative to the reference. So this has got to be for whom?
Dad.
That's dad's, right? Because he's not a kid and he's not a mom, so that's the only thing that's left. So welcome to Mixed in Stata. This is what we will use in the longitudinal class as well. What outcome are we predicting? The combined column called marital that has all three people's outcomes in it. I'm predicting it from kid and mom dummy codes only. My identifier variable for which rows should be grouped together in the R matrix is family ID. I do not want a random intercept for this yet. No log means suppress extra parts of the output that in terms of the iteration history. Residuals. Okay, so this is new. This is an unstructured R matrix. Do you remember what kind that is? Everything gets to be what it wants. So 3 separate variances, 3 separate covariances is what we're asking for. And in Stata, for whatever reason, unstructured matrices go really, really slow. I discovered this the hard way when I was building the website for my book, that the same models that would converge instantly in other programs, it'd be like hours in Stata. And I was going through the manuals and trying to think, is there a way to fix this? And I kid you not, I found this option. Difficult. Like, this model is hard, make it easier. I have no idea what this does, but I've just started like superstitiously adding it to things to see if it helps, and it seems to. So it's difficult. Why is that not a default? I don't know. But I've done some crazy models that take like days to converge, and then they take like a half a day if you call them difficult. So, anywho. Then I get the 3 things I'm asking for that are not given directly. So what is the intercept going to be for moms and kids? It's the dad plus the difference. And then what is the difference in the intercept between kids and moms? It's one slope minus the other. Here's my output. So I get an F-test by default that tells me if the 3 condition means are different, so 2 degrees of freedom there. Here is a new set of output that you probably would never paid attention to before, even if you've seen it. This is the output for your model for the variance. So this var E1, that is the variance of the first outcome, which I think is kids. E2, I believe, is moms. Oh, look, I knew that I would need to know that. Yeah. Past Lisa knew future Lisa would be tired right now. And dads. And then we get all the covariances. And if you're like, hey, I don't like covariances, can you turn those into correlations? Yes, I can. So SStat W correlation shows the correlation matrix. So this right now is the correlation across these 3 outcomes. The model lets it be different. It looks like, just eyeballing it, that these variances are largely similar, but maybe there's a little more variance across the kids. Those are testable hypotheses. In R, here's the same model. So GLS is a new routine that you haven't seen yet. It stands for generalized least squares. It was the only thing I could find that had different patterns of R matrices and would allow you to not have random effects at the same time. So in this one, it's not formula, it's model. Marital is the 1 column. Here's the 1 for the general intercept that applies to everyone plus the 2 dummy codes. And, wait for it, this is how you tell it unstructured. There's not just a word that you can type, like in Stata, you can just say unstructured, or UN actually, you don't have to type the full thing. So I don't know what this means. I'll just tell you that. I found it, it worked, the end. That's it. It means unstructured, that's what it is. Also, weights equals this. That's how you tell it you want different variances. I don't know what that means either. I don't. Internet, if you know what it means, please tell me. I am very good at finding patterns and working with patterns. But that sometimes means I don't know what the pattern is, what it means. Here is the correlation structure that's given first. These are multipliers that are used to multiply the standard deviation relative to the first DV. I had to figure that out the hard way. It's not helpful. Just ignore it. Instead, I learned how to get it to tell me what the R matrix looks like. So I have get varicove, and then this is the first person in my data set for that variable. That's where that number came from. And then core matrix is the correlation version. So the same numbers that we saw in this data output in a list like this, they are filling up this matrix. So this is the variance for kids, this is the variance for moms, this is the variance for dads. These are the covariance between each pair, and then these are the corresponding correlations. So this is the pattern that we're saying we have. It can't be wrong. Then to figure out if we have mean differences across the three types of people that we have here, the same test that was given by default in Stata, you have to ask for. So I learned how to do that. It's our friend GLHT. We've used them before. We'll use them in the longitudinal class as well. And I'm asking it to bind together the slope that differentiates moms, or is it kids or first? Who's first? Kids first, okay. Then this one is the slope that differentiates kids from dads, and this one is the slope that differentiates moms from dads. The fact that I've got a comma in here means do a joint hypothesis test of both of these slopes at the same time. So that is a very long-winded way of saying, are there any differences across the three DVs and their means? That's what I want to know. And then it generated an error message that said, I'm not going to give you the F-test, no. I'm only going to give you a chi-square. Well, chi-square divided by 2 degrees of freedom is my F. That is the 16. And I was like, all right, I don't believe you are. I bet it's in there somewhere because it's the right answer. And lo and behold, an hour or two of searching later, I found where it was buried inside the saved object, and I was like, print it. And I got it. So, I win. I don't know why I was like, I'm not going to give it to you. I'm just not. You have it, though. You made it, and you saved it as an object. So that's the test statistic. That's numerator degrees of freedom. That's denominator degrees of freedom. And that is the p-value that goes with it. So, nah. And then here is the missing pieces that we don't yet know. So what would the kid-intercept be? I need to add together the general intercept plus the kid difference. What is the mom-intercept? I need to start with the dad-intercept plus the mom difference. And then kid versus mom is the difference between those two. 0 minus 1 is minus 1. 1 minus 0 is 1. All right. There. Here's the answers in SAS, because their tables are a lot more compact for everything. So the fixed effects, here's the dad mean. That's the dad intercept. Here's how much kids differ from dads. So it looks like on average they are less conservative. Here's how moms differ from dads. They are about the same, slightly less conservative. Here are the predicted means on the scale for moms and kids. And then moms versus kids is comparing that difference to that difference, and it looks like there is a difference, so kids are less conservative than moms as well. There. Okay, only one empty model, because it's 312. So, but you know where I'm going. Can I just have 3 means? Yes. Then your output is the mean for each, period. It's better, right? It's much better. So this is what we're going to do it this way. All right, questions before we call it a week, not just a day. All right then, let me know if you need anything. Homework, nope, formative assessment, next one, 5, due on Monday. Otherwise, have good weekends. Thanks for being here. Safe travels if you're heading out.